Find the 8 roots of 1 and graph the roots in complex plane. The 8 root of 1 is 1 to the 1 over 8 power. This is the same as the solution of z to the 8 equals 1, so that z equals 1 to the 1 over 8, or the 8 root of 1. We know that in complex plane or complex system, there will be 8 distinct solutions, so it will not simply be 1. The answers are in complex plane now. To find the 8th root, we will use the n roots of complex numbers. We state that if the complex number z equals r cosine of theta plus I sine theta, then the n root of z is the n root of the modulus r times cosine of theta plus 2k pi over n plus I sine of theta plus 2k pi over n, where k is an integer starting at 0, 1, all the way to n minus 1. So in this case, with n equals 8, we will use k equals 0, 1, 2, 3, 4, 5, 6, 7. There are 8 distinct roots when we're done. Z is simply 1 in this case, or 1 plus 0i. And in complex, we need to find r. r is a squared plus b squared, the square root. The real part for 1 plus 0i is 1, and the imaginary part is 0. So the modulus r is 1. Theta is simply 0 in this case because tangent of theta equals b over a, which is 0. So theta is 0. The complex number z equals 1, which is a real number. In polar, it is 1 times cosine of 0 plus I sine of 0. Don't simplify it, even though sine of 0 is 0, but we will need this to use the formula for the n root of complex plane. For the general formula, we have the 8 root of 1 equals the 8 root of the modulus 1 times cosine of theta, which is 0, plus 2k pi over 8, n is 8 in this case, plus I sine of 0 plus 2k pi over 8. And again, n is 8, and that 0 comes from this argument of z. When k equals 0, we have the first solution, z sub 0, is the a root of 1 is 1, and then we have cosine of 2 times 0 times pi over 8 plus I sine of 2 times 0 times pi over 8, where k is 0. This is cosine of 0 plus I sine of 0, but cosine of 0 is 1, as expected. When k equals 1, we have z sub 1 equals the a root of the modulus, which is the real number, is still 1. Cosine of 0 plus, we don't need to write 0 plus, but this time k is 1, so we have 2 times 1 times pi over 8 plus I sine of 2 times 1 times pi over 8, which is cosine of pi over 4 plus I sine of pi over 4. And this is root 2 over 2 plus root 2 over 2i. When k equals 2, we will speed this up. Z sub 2 equals 1. K is now 2, so we have cosine of 2 times 2 is 4, 4 pi over 8 plus I, sine of 4 pi over 8. And this is cosine of pi over 2 plus I, sine of pi over 2. But cosine of pi over 2 is 0, and sine of pi over 2 is 1. So this is simply I. If we keep doing this, replacing k equals 1, 2, all the way to k equals 7. Remember that we start with k equals 0 and we end up with k equals 7. Z sub 7, which is the 8th root already, it is 1 times cosine of 2 times 7 is 14. 14 pi over 8 plus I, sine of 14 pi over 8. K is 7, so 2 times 7 is 14. This is cosine of, divided by 2, top and bottom, we have 7 pi over 4 plus I, sine of 7 pi over 4. But cosine of 7 pi over 4 is positive root 2 over 2, and sine of 7 pi over 4 is negative root 2 over 2. So this is root 2 over 2 minus root 2 over 2i. And again, k equals 3, k equals 4, k equals 5, k equals 6, all the way to k equals 7. If we graph this on the circle, we will see that for the first solution, it is simply 1, or at the point 1, 0. This is the first solution, z sub 0. For root 2 over 2 plus root 2 over 2i, it is the second solution, z sub 1, with the angle pi over 4. The third solution, z sub 2, is at the angle pi over 2. And if we plug in k equals 3, we will see that the next solution is in the second quadrant, z sub 3, which is the fourth solution at the angle 3 pi over 4. If we plug in k equals 4, we will obtain the solution at exactly pi for z sub 4. And the next one, z sub 5, is at the angle 5 pi over 4. Z sub 6 is at 3 pi over 2, and z sub 7 is at the angle 7 pi over 4. It is the 8th root, so it partitions the circle into 8 equal pieces of the equidistant equals angles.